Imagine a world where machines don't just follow instructions, but understand context, reason through ambiguity, and generate ideas as creatively as a human. That world isn't science fiction. It's unfolding right now, driven by a revolution in artificial intelligence, the rise of large language models. But here's the thing, most people still think of AI as just chatbots or text generators. They're missing the real story. Behind every viral AI response is a complex architecture built on decades of research, pushing the boundaries of how machines process language, learn from data, and simulate cognition. Let's go deep. At the heart of modern large language models lies the transformer architecture, a breakthrough introduced in 2017 by Vaswani et al. In the paper, attention is all you need. This wasn't just an incremental improvement. It was a paradigm shift. Before transformers, sequence models like RNNs and LSTMs processed text one word at a time, in order. They struggled with long-range dependencies, remembering what happened at the beginning of a sentence when they reached the end. They were slow, hard to train, and limited in scale. The transformer solved this with a single, elegant innovation: self-attention. Self-attention allows every word in a sentence to dynamically relate to every other word, regardless of distance. It's like giving each word a mental spotlight, letting it weigh how relevant every other word is when forming its own representation. Here is how it works. When the model sees the sentence "the cat sat on the mat," it doesn't just process cat after the. Instead, it computes attention scores between cat and sat and mat, the and cat, and so on. These scores determine how much each word should influence the representation of another. Mathematically, this is done using three vectors: query, key, and value. The query from one word asks, "What do I need to know from other words?" The key from another word answers, "Here is what I have." The dot product between query and key gives the attention score. Then the value is weighted by that score and summed, producing a context-aware representation. And because these operations are fully parallelizable, unlike RNNs, transformers can process entire sequences at once. That's why they scale so well with massive datasets and massive model sizes. Now let's talk about training. A model like GPT-3, with 175 billion parameters, isn't trained on a single machine. It's trained across thousands of GPUs, often using a technique called mixed precision training, where computations are done in both 16-bit and 32-bit floating point to speed things up without sacrificing accuracy. The training data. Trillions of tokens scraped from the internet, books, articles, websites, code. This data is tokenized. Words are broken into subwords using algorithms like Byte Pair Encoding, BPE. So unhappiness becomes unhappiness, a way to handle rare or unseen words efficiently. But here is the key insight: the model learns patterns, not meaning. It doesn't understand the word cat in the way a human does. It learns statistical correlations, how cat tends to appear after the or my, how sat often follows cat, and how mat frequently appears after on. Over time, these patterns coalesce into something that mimics understanding. This is called emergent behavior. It's not programmed. It arises from the sheer scale of data and parameters. Now consider inference, the process of generating a response after training. When you ask, "Write a poem about autumn," the model doesn't retrieve a pre-written poem. Instead, it generates one word at a time, using its internal knowledge to predict the most probable next word based on what's come before. This is done through a mechanism called autoregressive generation. At each step, the model computes the probability distribution over all possible next tokens, then samples from that distribution, usually using techniques like top K sampling or nucleus sampling, top P, to balance creativity and coherence. But here is where things get subtle. The model doesn't decide what to say. It doesn't have intentions or beliefs. It's just following the statistical likelihoods learned during training. Yet the output often feels intentional, insightful, even poetic. That's the illusion of intelligence. So how do we measure success? We use benchmarks, like the MMLU, Massive Multitask Language Understanding, which tests a model's knowledge across 57 subjects, from law to molecular biology. Or the GSM-8K dataset, which challenges models with multi-step math word problems. But benchmarks have limits. A model can score highly on MMLU by memorizing patterns in the training data, not by truly reasoning. And when faced with novel or ambiguous questions, it can confidently produce plausible-sounding but incorrect answers, what we call hallucinations. This is why safety and alignment are critical. Researchers are now developing techniques like reinforcement learning from human feedback, RLHF, where models are fine-tuned based on human preferences. Humans rate model responses, and the model learns to avoid harmful, biased, or factually incorrect outputs. But even with RLHF, models can still be manipulated through prompt engineering, adversarial inputs, or jailbreaking techniques. A well-crafted prompt can trick a model into generating content it was trained to avoid. So what's next? The frontier isn't just bigger models. It's smarter ones. Researchers are exploring hybrid architectures, combining transformers with symbolic reasoning systems, or integrating external tools like calculators, databases, or code executors. Models like Google's Gemini and OpenAI's O1 series are beginning to reason through chains of thought, simulate multiple hypotheses, and verify their own outputs. There's also growing interest in efficient inference, making models faster and cheaper to run, through techniques like quantization, pruning, and distillation. A 7 billion parameter model can now rival a 70 billion parameter model in performance, thanks to smarter training and architecture. And on the hardware side, new AI chips, like NVIDIA's Hopper, Google's TPU V5e, and custom silicon from startups, are being designed specifically for transformer workloads, enabling real-time inference at scale. But perhaps the most profound shift isn't technical. It's philosophical. We're no longer asking, can machines think? We're asking, what does it mean to think? As models grow more capable, they force us to reevaluate the nature of language, cognition, and creativity. Are we building tools or something more? The answer may not lie in the model itself, but in how we use it. We're not just witnessing the rise of artificial intelligence. We're co-creating it, through the data we provide, the questions we ask, the values we encode. So the next time you ask an AI to write a story, solve a problem, or explain a concept, remember, you're not just talking to a machine. You're engaging in a conversation with the sum of human knowledge, reassembled, reimagined, and reinterpreted, not by a mind, but by mathematics, data, and design. And that right there is the real wonder.